Now, as we are through with the Lc oscillations, we shall try to understand some of the graphs which are really very essential in order to understand the resonance and as such the resonance circuits. The resonance circuits are basically of two types, the series resonance circuit and the parallel resonance circuit. But to understand that, first of all, let us recapitulate about purely inductive circuit and a purely capacitive circuit. Over there, in say for example in a purely inductive circuit, we have seen that the inductive reactance was directly proportional to the F or the frequency, right? So we can say that for inductive circuit, XL, which was the inductive reactance of purely inductive circuit, this was directly proportional to F. And as we know that the current or the value of the peak value of the current is inversely proportional to this inductive reactance, which means that I is inversely proportional to XL, which again implies that this I will again be inversely proportional to the frequency of the AC supply, because over here we could see that the inductive reactance is directly proportional to the frequency of the AC supply. So if we wish to find out the relation between this XL and F, and again if we wish to find out the relation between I and F, over here this will be the relationship between XL and F. And over here we shall be discussing about the relationship between the alternating current and the frequency, right? So as we see that XL is directly proportional to F, this XLF, we will see the graph like this. That XL over here is directly proportional to the frequency of supply or the AC supply. And the graph for I, which is inversely proportional to F, shall look like this. Right? Now, this is the scenario for a purely inductive circuit. Purely inductive circuit, and this is the relation between XL and F, and this is the relation between I and F. Now if we wish to see the relation in a purely capacitive circuit, we have seen over there that the capacitive reactance was inversely proportional to the frequency of the AC supply. Right? And as we know that the alternating current is again inversely proportional to the capacitive reactance, which means that now this alternating current will be directly proportional to the frequency supplied in the AC, right? So over here, if we wish to see the graph, first of all, for XC versus F, and subsequently we wish to see the graph of I versus F in a purely capacitive circuit. So as we see that Xc is inversely proportional to F, we could design the graph likewise. And as we see that this alternating current is directly proportional to F, the graph shall be like this. This is the case of a purely capacitive circuit. Now observe minutely the graph of the reactance. First of all, forget about the inductive or the capacitive. The graph about the reactance versus F is actually seems the same like I versus F. And the graph for reactance versus F over here actually looks alike like the I versus F. So, in the inductive circuit, if we do remember about the graph for this XL or the inductive reactance versus this frequency, we can simply put it out for a purely capacitive circuit as the graph of like I or the alternating current versus the frequency in a purely capacitive circuit and vice versa, right? So over here we have understood the relation and the graphical representation of the inductive reactance, the capacitive reactance, the alternating currents and the frequency of the alternating current supply. Now, as we have seen in Lc oscillations about the terms, there were two terms, U, C and UL. UC is, this one, UC is the energy associated with a capacitor. And we have seen the relation as Q square divided by 2C, and UL on the other hand is equals to half Li square. Now Q was the total amount of charge that was present initially at the very beginning on one of the plate of the capacitor, and C is the amount of the capacitance of those parallel plates. Over here L is the amount of self-inductance and I is the amount of current that is flowing through an inductor, right? Now, as we know the relation, as we have studied in earlier classes, like in earlier standards of say 9 and 10, we have seen a very important concept that potential energy plus kinetic energy was always constant. If we add up the potential energy plus kinetic energy of a person who is on the top of a hill, that, say for example, the value is X, and when the person came down to the sea level on seashore, again his potential energy plus the kinetic energy will simply be equal to X, right? This is the case of an ideal scenario. Ideal scenario, as we have discussed in Lc oscillation, means that there is no kind of resistance present, right? So in that scenario, if we do like to take also the graph, over here on this axis we take energy, and on this axis we take, say for example, the time, right? Initially, while we were discussing about, say for example, like the Lc oscillation, over there we have seen that initially UL was equal to 0 and at that time UC was maximum. So let us keep first of all the UC as maximum over this level, right? Now, as we have seen the graph over there, the relationship between the Q or the charge with respect to time in a purely like ideal situation when there is no resistance of the inductor or the current carrying conductor, right? This will be like this. Right? This is the graph for UC. UC. Now, as we know that on the very first occasion, UL was equal to 0. After that, it goes to the medium level and then it reaches to the highest maximum point. Now, when did it actually reach the highest maximum point of the UL? Yes, at that point when UC was equals to 0, right? So, we could make it as such. Like this. We see that when the UC was maximum, UL is 0, then it rises, and over here when we see that UC becomes 0, then UL will be the maximum. Again over there from that point it will start to decrease and it will see that this UL will come to 0 when we will see that this UC is the maximum. Again this UL will start to increase when we will see that UC is going to decrease, and this will become the maximum at this point when again we will see that UC is 0. First of all, these graphs are continuous graphs, right? No sharp edges. And this over here, this is actually UL. Now, at any point of time, if you find out the value of UC plus UL, you will get this amount of energy. This amount of energy we are going to get throughout. Say for example, at this particular point, UC is equals to this, right? Say this point as, let us say it for P. At this point, UC is equals to P and UL is equals to 0. So at this particular point, UC plus UL will be equals to P, right? At this point, see, UC is equals to 0, but UL is equals to P now. So UC plus UL will again be equals to P. Likewise, the point for over here and point for over here. Now, what will be the scenario of over this region or this region? At any particular point, if we find out, for example, we are going to find out at this point. See, at this point, particular point, at this particular time interval t, we will see that, for example, this value is equals to x and this value. The x is the value for UL, and say for example y now is the value for this UC. Now if we are going to add up UC plus UL at this particular point of time, then obviously we shall find it as x plus 1. Now whatever may be the case is, whenever you are taking for the time, you will find that this x plus y is equals to p. This is one of the important characteristics of this kind of oscillation, where you will always find that this line of P is basically, this indicates UC plus UL, and that is the energy where it is conserved always. The energy over here actually shuttles back and forth from the electrical, like the electric field of this capacitor to the magnetic field of this inductor and vice versa, right? Now, if we are going to take over in the situation of Lc oscillation, that XL or the reactive, like this XL over here, the inductive reactance, this inductive reactance becomes equal to the capacitive reactance, right? If we take up this case of the Lc oscillation, in Lc oscillation, then if we are going to equate it, we know that XL is simply equals to L omega, and this XC will be equals to 1 divided by C omega, as we have seen it earlier. Now, if we are going to perform, we will see that omega square is equals to 1 divided by LC. Or now we know that omega is equals to 2 pi f, where f is the frequency. So we can get that 2 pi f whole square is equals to 1 divided by LC. And if we wish to find out only this f, this expression shall look like 1 divided by 2 pi under root of LC. Now this frequency is actually the frequency of the Lc oscillation. Remember, for the lecture of Lc oscillation, it was mentioned that after case 1, case 2 happens, the figure 3 happens, figure 4, but after the figure 8, the figure 9 will look same as figure 1, as we have discussed over there. And it was mentioned that after every regular frequency, it happens. Right? After every regular time interval, it happens, which means obviously there is a frequency associated, right? This is the frequency what we are discussing about. This frequency is known as, like we could tell it as a frequency for Lc oscillation. And we will also see that how this frequency actually comes in the concept of resonance, let it say as series, like resonance in series circuit or resonance in parallel circuit. So watch out for the video of the resonance circuit. Thank you. Hello and welcome to today's interesting topic of series resonance circuit. Now, first of all, to understand the series resonance circuit, we need to understand the term resonance. Now, what resonance basically, what resonance basically is about? Resonance means that it is a property like a system of, say, for example, LCR, right? The LCR circuit is in series. A system, or the tendency of a system to oscillate more with a higher amplitude at certain given hour frequency or at some selected frequency more than other frequencies is known as resonance. So, for example, we take at frequency of say 40 Hz, the system over there, the current, okay, it is oscillating because the current oscillates like in a sine wave form. The current actually, for example, the value of the current is say 20 ampere. At 50 Hz of frequency, the current becomes 100 ampere. And again at 60 Hz, the current becomes, say, for example, 20 ampere. So 20 ampere, 100 ampere, and then 20 ampere. So at the selected frequency of, say, 50 Hz over there, we noticed that the oscillation is over there, like it has oscillated with the greatest amplitude. So the resonance, we could tell it that the tendency of a system to oscillate more than oscillate more at a given certain frequency, which obviously is known as the resonant frequency, more than at other frequencies is called resonance. So now let us come and look at how the things actually are. First of all, this is, say for example, the AC supply, right? And over there it is connected. Say for LCR, this one is an inductor, this one is the capacitor, and then a resistor over here, like this. Now, say for example, the current flows over here, I. It goes like this, comes back in this way. Now, for this particular thing, if this is, say for example, L, C, and R, the respective, over here we could see that, say the voltage over here, say for example for this it is VL. Over here we can observe that this is the voltage due to the capacitor, the VC, and for this resistor we observe the voltage as VR. Right? Now, as we have seen that for this inductor there is a certain inductive reactance called XL. For C it is XC on the inductive capacitance, and for the resistor it is simply R or the resistance. All this XL, XC and R, they are calculated in terms of the SI unit of ohm, right? So let us try to draw a graph that it will be like in ohm, or the reactance is in ohm versus the frequency at different levels. So if for example we draw a graph like this, so say for example the graph is over here like this, and over in this axis we maintain reactance and so only reactance and frequency for the time being. Afterward we will see that how in a different graph that how we can draw the VI individual graph with respect to the frequency. So concentrate over here. If this reactance is measured in ohms, if this is measured in ohm, this reactance, first of all, there will be a resistance of R, right? Say for example, we denote this R with red ink, the mark of R. As we have seen earlier, that this R actually does not change with the change of frequency. That is the reason why in this reactance of this R versus the F graph, whatever be the value of this frequency F, R will remain constant, right? So we are denoting this R by the red line. Now, for XL, we have seen in the previous lecture that XL was a straight line like this, right? So let us make it likewise. This is XL. We are denoting XL by this black ink. So we can write as this is, say for example, XL. This is R. XL is what? This is inductive reactance, and obviously this is the effective reactance that is being offered by this L. So it will be measured in ohm, right? Now the left out C, for this C there will be a capacitive reactance, right? Now let us show the capacitive reactance with the help of this blue line. As we have seen that XC, the graph of XC was somewhat like this. So let us draw the graph. Somewhat like this. This is what? XC. Now we have actually plotted all XL, XC and R in the same graph, right? With their reactance in ohm versus the frequency. And as we know that XL and XC, they actually vary with respect to this frequency. They are dependent on frequency, whereas this R was independent of the frequency. That is the reason why it is a straight line, right? Now observe minutely the situation. At this particular point where this XL and XC actually made together. So if we make this on the perpendicular, the projection, if we make the projection perpendicular to this axis where it contains the frequency, which is obviously measured in the SI unit of Hertz, we will see that there is a particular frequency, right? So let us denote this particular frequency by Fr. Okay? And if we denote it by Fr in this particular scenario, now let us try to make the graph of XL minus XC, right? Now the graph of XL minus XC will be somewhat like over here. It will be like this. This graph actually means XL minus XC. Now we want to understand it, that why the XL minus XC graph will look somewhat like this. Observe at this particular point when the frequency was Fr, the value of XL and the value of XC was same. The reactance of XL, this is a reactance of, say, this XL, and this is XC. The value of them is same in terms of ohm. So if we are going to find out the curve for XL minus XC, we will see that at this particular point XL cancel out XC. That is the reason why it is 0 over here, because this is the origin, right? And if it happens as such in this scenario, we can tell that at this particular point of Fr, we shall say that XL is equals to XC, which means at this particular point we could say that L omega is equals to 1 divided by C omega, or which means that we can state it as omega is equals to 1 divided by LC, and as this will be omega square. And what is the value of omega? As we know that the value of omega is equals to 2 pi f. So at this particular frequency f, or what is known as Fr, we shall find that this Fr is equals to 1 divided by 2 pi under root of LC. Again, this is an ideal situation where there is no resistance of this inductor. There will be inductive reactance. That is a different, completely different part. But the material of which this inductor is made of, that is simply admitting the current to infinity, which means that the resistance of the material by which this inductor has been made is 0. Right? But it has got an inductive reactance that is equals to L omega, and we did find out over here that at this Fr, where we were saying that XL was cancelling out this XC, which means that this Fr will simply be equals to 1 divided by 2 pi under root of LC, where L is the value of the self-inductance and C is the value of the capacitance. Right? Now we have found out that what is actually Fr, what will be the value of Fr for the given L and C. Right? Now, if this is XL minus XC, we know that Z LCR, which means that the impedance of this LCR circuit, right, it is basically equals to under root of R square plus XL minus XC square, or L omega minus 1 divided by C omega whole square. At this particular point, we did find out that XL minus XC is equal to 0, which means at this particular point, ZLCR at Fr, we could write it at under root of R square plus 0 square, which will be simply equals to R. Which means that the impedance of this LCR circuit at this given particular frequency, which is also known as Fr, or the resonant frequency, over there the Z is simply equals to R, which means that actually the L and C are not actually opposing this current, right? Otherwise the value would have been greater than R. Now since this is 0, now whatever this is happening in L and C, they are cancelling out each other, which means that the current that will flow will now only be opposed by this resistor simply and none else. And if this is the scenario, this means that now this LCR circuit is just converted into a purely resistive circuit, which means that in this particular area, it simply seems to have disappeared. And if it simply seems to have disappeared, we could say that at this particular point, within this part of the circuit, a short circuit has happened. Right? Now, over here, as we could see that the ZLC will be equals to R only at this frequency given. So if we wish to find out the graph for ZLCR, so it should look like at this particular point it will be equals to R, which means this point only. So it will look like over here. This will be the minimum value of Z, because the minimum value of Z will be when XL equals to XC, that will be simply equals to R. At this R it will be, and afterwards it will be rising from over here. Right? So this curve we could say as the curve for ZLCR, or the like the impedance or this LCR circuit. Now we have found out over here XL, XC, R, XL minus XC and the Z, that what will be the actual resistance being offered by this entire circuit at this resonant frequency will simply be equals to R, and this resonant frequency is being determined the case when this XL and XR cancel out each other. Right? Now, if we wish to draw another graph, say for example in this graph we wish to find out V and I respectively on this axis, and again over here the frequency in hertz. Right? Simply we know the voltage is equals to current multiplied by the resistance or the reactance that is occurring. So see, if the reactance is on, say for example like XL, if this reactance is going up, it is increasing, then obviously the value of that IR, where I, this will be not R, this will be I multiplied by XL, will also rise. The voltage shall also rise. So the voltage for this L, this VL, will be simply like this curve. Right? So we can make the VL graph as such. So this will be VL. We are denoting this L by this black line. Now, for this XC, again it will happen the same, because the voltage at this C, this one, the voltage at this C will simply be equals to the I multiplied by XC. And if it is decreasing with time, the voltage shall also decrease, because the multiplying factor with I is decreasing. Right? So this will be the scenario for this voltage of C. Say for example the voltage of C. And if this R is remaining constant, then obviously the voltage of R shall remain constant. Right? So this will be the voltage of R, this VR. Now, over here we could see this was the particular point. If the projection is being made on the frequency, we will see that this is the particular point, FR, where actually the VL and the VC cancel out each other, which means that the voltage due to this inductor actually is equal to the voltage due to this capacitor. We are saying this for V, right? Which means that for, as we have seen, say for example we take it like this. See over here, this green line actually is representing the VL, and this VC, as we know that the voltages of this inductor and this capacitor are simply outphase, which means they are simply in opposite direction. So this will be for VC, the direction will be as such. And let us mark this as VR. Now what will be the resultant due to this? When we could see that this VL is actually equal to VC. S is trying to pull hard, this is also trying to pull hard. 5 Newton of force in this direction, 5 Newton of force in this direction as well. What is the displacement of the object? Simply 0. So, the resultant of VL and VC will be equals to 0. The only remaining thing is VR. So, in this certain scenario, the voltage of this LCR or the system, this is the system, the voltage of this LCR will start acting like the voltage of the resistor. This. But when? At this particular frequency only. Right? Not at other particular frequencies. So, if we do see over here that this one at this particular frequency, this is voltage R, that VR. So at this point, this will be the minimum case of the voltage of LCR, VLCR, right? So like the VLCR, we can say it likewise, right? So the graph will be somewhat like this. This will be the minimum point when this V of LCR will simply be equals to VR, right? So this will be V of LCR. Now, two concepts. Over here, see, we are going to draw now the I, the current. See over here, if this is the Z of LCR, this red curve, which means that this is actually the impedance offered by this LCR circuit, or actually the resistance to the flow of current, right? But this impedance is very less, or the least or minimum at this point. And what is this point? This point is simply the resonant frequency. So at this resonant frequency, when we observe that the impedance of the LCR circuit is the minimum, then obviously the current flowing through it will be the maximum, right? So the line which is now being represented by the red line will show the current. So this will be somewhat the characteristic of this line, and this line is the basically I, right? So we could see that at this particular frequency of Fr, which is known as a resonant frequency, we see that the I is a maximum. But this is the scenario when there is the series resonance circuit, which means that LCR is now in series combination, wherein we have seen that this particular frequency is being observed when the XL and the XC actually cancel out each other, or the VR or VL actually, the VL and the VC actually cancel out each other, which means that this is the case. And also, if this is the scenario of this particular FR, at this particular moment, the I will be in phase with the VR, right? So I will be like this. The value of I will obviously be the value of this R at this particular point divided by the impedance or ZLCR, as we know. So over here we could say that this I is smaller. If this is the phasor diagram, I will be smaller, but I and this VLCR at this particular portion, at this particular instant when the frequency equal to Fr, they will simply be in phase, right? So the difference of the phase angle will be equal to 0. Okay. So in these circumstances, we have understood that this is a resonant frequency over here, where actually VR is equals to VL, where actually the VL is equals to VC, and the XL is equals to XC, and likewise how we could find out the Z of LCR, and the Z of LCR is basically equal to R at this particular point, right? Now over here, as we see that the amount of the current is maximum in this particular thing over here at this resonant frequency, we could also term this series resonance circuit as acceptor circuits. Right? And the utility of this acceptor circuit or series resonance circuit is that we could write it as, for example, the utility or the application. Utility of this is that they are used in constructing high frequency selective filters. But it must be noted that if this is the scenario, I is at its peak position, then we could actually damage that. For example, we are utilizing this circuit, we could actually damage the circuit because the flow of I, when this is the short circuit or VL equal to VC, at this particular point of time the I will be the maximum, right? So they are only used in various applications, keeping in view that the I will be maximum. And the utility, one of the utility is they are used in constructing high frequency selective filters, as they are also known as the acceptor circuits, right? Thank you. Now in this particular lecture we shall be understanding about the qualitative study of the Lc oscillation, where L it is the inductor and C it is a capacitor, right? Now how are they connected? They are connected obviously in series. Let us check it. Over here there will be an inductor and there will be a capacitor. Right? The value for self-inductance of this inductor will be equal to L, and the value of capacitance of this capacitor will be equal to C. Now in this particular scenario, if we take that initially a charge of, say, capital Q is already present in this capacitor, then the scenario will be like this. Right? Now, what will happen over here is that, see, there will be an I, an alternating current in this like inductor L, but initially this I will be 0. So over here for this case we can say that the I in this is 0, right? And Q is the total amount of charge that is present in the capacitor, right? And as we have seen that over here the energy of the capacitor will be the maximum, right? And the energy of the inductor will be equals to 0 or minimum, right? How could we say that? Because as we have seen in the previous lecture that EC over there was equals to Q square divided by 2C, and over here we have seen that the energy associated with an inductor is equals to half Li square. Now observe, if I over here is equals to 0, then obviously EL will be equals to 0, right? Or it will be the minimum. And the EC over here will be Q square divided by 2C, because the total amount of charge, the Q which is present over here, will be. So we can say the amount of charge that is present now will be equals to capital Q, right? This is the first scenario. Second, now what will happen is that this charge through the capacitor, it will start to get transmitted or transferred through the inductor. How? Just the next stage to this, we can say it likewise. This is the capacitor and the inductor over here. If the arrow was like this, we know from electrostatics the principle while we discussed about the C, or in electrostatics when we studied about the capacitance, right? We know that that current or I will start flow in this direction. And as such, the Q over here which is present will say decrease. Say for example, now let us over here, there was 4 lines, now let us represent by 2 lines, right? Now we will see over here the scenario as we have seen in the cases of self-inductance. We will see the scenario likewise. As such, like this, where the value is L, right? Now over here we could say that an amount of current or I now is present, as we could see, and the Q which is present in the capacitor will suddenly be now lesser than the total amount of Q that was present in the first case, right? And we could see that the energy stored in the capacitor will now not be the maximum, right? It will be like medium. Let us say it as medium, right? And the EL, obviously there is the presence of I, so EL will have a certain value. The EL will also obtain a medium value. Why not maximum? We are going to see just in the next scenario. So this is the second case, right? The third case, it shall be like this is the inductor, the capacitor is connected to it. Now the discharge of this Q has been exhausted and there is no Q present over here right now. So there will be no arrow, right? So we can say that by self-inductance, the scenario at the inductor will be like this. Right? Because the electricity or the alternating current is now flowing like this. In this scenario, observe carefully that I will certainly increase, and just because of that reason, we could say that I is present, but now the Q is equals to 0. Observe, first of all, I was equals to 0, but there was capital Q. Now it changed as such that now I is equals to, like, it is maximum, and Q has become 0, right? So we can say that the energy of the capacitor now, there is no Q, EC will simply be equals to 0. So this is the case of the minimum energy, right, for the capacitor. And now for the inductor, the energy associated now will be the maximum. As you could see over here, this is medium, and now over here this is maximum. And this is the third case. Now, closely observe that these charges are now going to move from the inductor to the capacitor via this path, right? So the fourth scenario, what we shall observe will be obviously due to, like, say for example, due to self-inductance, the scenarios will now be like this, as because I is flowing, and thus the charge is now carried to the capacitor. This is L, this is C. Now it will be as such that some of the charges has reached on this plate. Say for example, first of all observe that this charge which was present on the upper plate, now it is getting transferred now to the lower plate, right? So this is the fourth scenario over where we can say, obviously yes, there is a current, an alternating current. So we can say that I is present, but Q is lesser than this Q, because this is the maximum of 4 lines, but over here we see 3 lines. So obviously the amount of charge will be lesser than the total amount of charge that was present initially. And now we will observe the EC, or the energy associated with the capacitor. Yes, there is at least some Q, so there will be at least some EC. So we can say that it is medium, and EL over here, see, this has reduced. So we can say that EL now is not maximum but medium in this case. And if this is the medium, then we can say that this is the fourth scenario. Now in the fifth scenario, we shall see like this one. But now all of the charges from this upper plate is now transferred to the lower plate via this inductor, right? So we can say that now Q, the total amount of charge that was present initially, came back to the other plate now. So there will be no flow of I. So I now will be equals to 0, and the Q that is present will be equals to capital Q. And if I is equals to 0, obviously the EL is going to be 0, and if it is Q, the EC is going to be the maximum. So the energy associated with the capacitor now will be the maximum, and the energy associated with the inductor will be the minimum or the 0, right? This is the fifth scenario. Now it is very interesting to understand the next scenario. Observe that just as this, from this step to this step, it had happened, again there will be a happening like this. But the only difference is that, as we have seen in electrostatics, this is reduced, right? So obviously there will be an I present, and obviously the Q now will again be lesser than this capital Q which is present over here, and The energy associated with the capacitor will now be again medium, and the energy associated with the inductor will again be medium, as we have seen over here. Just the same. The only difference is that now, as we have seen earlier, that this current was flowing counterclockwise. Now we will see that this is flowing in the clockwise direction. Why? Because see over here we have seen that the charge is present on the upper plate, so the current has started flowing from the upper plate. Now the charges are actually present in the lower plate, so the current will start to flow from this lower plate. So like this over here, in the clockwise direction, And if it is in the clockwise direction, again due to self-inductance, things will happen, but in the opposite direction. Right? So we can say this is the sixth scenario. Now, after this, what will happen? After this, we shall see the situation like this. Over here, the total charge is now transferred, because if this and this are analogous, obviously this and this will be in analogy, and there will be no charge present, and there will be the total things happening in this inductor. So we can say it like, due to self-induction, first of all, the I will be present, but the Q will simply be equals to 0, and if the Q is simply equals to 0, the EC will be equals to 0 in this scenario, and subsequently the EL will be the maximum, right? And if it happens, we will see right? Just in analogy, but the current will be in opposite direction, as we can see. This is anti-clockwise, this is clockwise. So the current shall start to flow from this. So this is the seventh scenario. Now, after this is the seventh scenario, again what will happen? As we have seen from over here, now the charges are going to get over here. We have seen that the charges were on the upper plate. It now totally went to the lower plate, right, after this, because over here, see, after this scenario, after this third case, on the fourth case we have seen that the started now, the charges over here were on upper plate, now it is on the lower plate, right? So obviously over here, if it is on the lower plate, this will again go on the upper plate. So the eighth scenario will be this is from the lower, now it will be from the upper. Why? Because these charges are now actually carried by this inductor, like it flows. These charges are actually transmitted via this inductor, right? So we can say over here in this situation, I is present, Q is present but obviously lesser than Q. Likewise, see, over here, this over, it has remained in the same direction. So likewise, this will also remain in the same direction likewise. Okay? But this will decrease as in comparison to the previous case. So we can say if some like charge is present, so the energy associated with the capacitor will be medium, and if I is also present over here, as such the Q is also present in the capacitor, we could also say that the energy associated with this inductor is again medium. This is the 8th scenario. Now, can you say that after the 8th scenario, what will happen? Very simple. After this 8th scenario, the 9th scenario will start looking like this. Because if this 8th scenario is just analogous to this one over here, see, this is 3, this is 3. And after that it has shifted such that there is no current. Obviously, over here there is current going in this direction. So just after over here, if this is an analogy, 8th scenario is an analogy to the 4th scenario, obviously the 9 will look somewhat like this. But this is the charges are on the lower plate. But over here, see, the charges are now going to get over on the upper plate. And what is the scenario of the upper plate? The first scenario. So after the 8th scenario, the first scenario will again take place. So we can say this as the 9th scenario. Now closely observe, as we can see, the energy of C and the energy of L. The energy associated with the capacitor and the energy associated with an inductor. If the energy associated with the capacitor is over here, the maximum, the energy associated with an inductor will be over here, the minimum. As this energy associated with the capacitor starts to decrease, the energy associated with the inductor will start to increase. There will be a situation when both will be at the same level. And after that, it will happen that this energy associated with the capacitor will decrease to 0, and the energy associated with the inductor at that time will rise to its highest point or the maximum. So it happened like EC maximum, now EC medium, now EC 0. Just the opposite. EL 0, EL medium and EL maximum. So at this situation where you found out that EC and EL both are in medium, which means that they are now in this or like this, right? But always in these scenarios, in ideal cases, right, we will find out. Ideal cases means obviously there will be only L and C, no R. I mean to say there will be no resistor with or no resistance, right? In the ideal cases, we will find out that the value of EC when it is added up with the value of EL at any point of time will be a constant, right? So this maximum plus 0 will give us the same value as the medium plus medium, or this 0 plus maximum. They will all give us the same value provided in ideal circumstances where there is only L and C and with the absence of any resistance, right? Now, for example, over here we could see that basically the energy is like it over here. See, the energy of C is now being transferred to the energy of L total, and after that this energy of L is again being transferred to the total of C, and again the energy of total C is transferred to the energy of L. Likewise, so basically in the inductor there is magnetic field, and in the capacitor, as we could see, there is the electric field. So in LC oscillation, the main thing what we could understand is that there is a constant like shift to and fro, constant drift or constant transfer of the energy from the like electric field of a capacitor to the magnetic field of the inductor, and vice versa. Like the magnetic field, the energy is transferred from the magnetic field of the inductor to the electric field in the capacitor, right? So if we try to draw the graph, it shall be like this. Say for example, if we try to draw the graph, over here we take Q, and on this axis we try to take the time. In ideal situation, when there is no resistance present in LC, this kind of circuits, obviously we shall find the graph as such. Like this, where it may be noted that if this is the amount of highest Q naught, or this is the highest amount Q, this will just remain the same. Q in this case, Q in this case, the maximum cases will have Q. But in practical, in real life, this is not true. Why? For example, you take a pendulum, right? And over there, you just keep it like this. This is the height at 0. You now take it to a higher point. So the bob of this pendulum will gain some height, right? So there will be a potential energy. Now if you release this bob, this will oscillate. Over at this point, the kinetic energy will be the maximum, but the potential energy will be 0. But this kinetic energy now will try to lift this bob again higher, such that in this position the kinetic energy now becomes 0, but the potential energy again became maximum, which will again throw the bob like this. This is like an oscillation. Same applies for this scenario, and that is the reason why this is known as LC oscillation, right? Inductor capacitor oscillation in an AC circuit, right? Now, have you ever imagined like if you were going to like displace this bob, this will simply go like to and fro, to and fro, to and fro forever? Have you seen this case? No. And you could not, because there is some friction of air. So after a certain point of time, you will see that the amplitude is decreasing and finally it will come at rest. Likewise, in every LC oscillation, there is negligible resistance, but yes, negligible resistance does not mean zero resistance. That means some resistance is there. So, this is the graph of like an ideal situation, but in real life, the graph will be like this. If we take over here this as Q, and on this axis if we take the time, then the maximum, as we have seen over here, this Q, this will start to decrease. Likewise, over here also, this will start to happen due to the so-called negligible resistance. Not zero, but there is some resistance, the negligible resistance. So, this graph will start likewise. If we take from over here, this will be, say, like this. It will go. So, this is the actual graph. Now, as we have seen that after a certain interval of time, this bob from this position comes back again over here. This is known as the frequency. Likewise, over here we could observe that after each 8 step, 1, 2, 3, 4, 5, 6, 7 and 8, after each 8 step, it is again coming back. Which means that this coming back is dependent upon the frequency, right? And depending upon this frequency, actually it comes back again to the previous step, right? Thank you. Now, as we have seen the resonance in series circuit, now we shall be looking into the parallel circuits, that how the resonance occurs, at what frequency the resonance occurs, and what will be the amount of current that will be flowing at the time of the resonance, right? So, let us check, like this is an AC power supply. Over here, we are connecting the L, C and R in parallel and not in series this time. So here we can see that actually a resistor, an inductor and a capacitor, they are all connected in parallel to this circuit, where we can say that this is, say for example, the potential drop for this particular LCR circuit. And as we know that if this are in parallel combination, then this potential drop of this VLCR will be applied and be seen in all the 3 scenarios, right? Now, applying the junction rule, if we do see over here that actually this is the I flowing, obviously we shall see that this is, say for example, I2, then this will be I1. We can say that I1 plus I2 is simply equals to I. And say for example, let us give it as IR, because this current, amount of current is actually passing through the resistor of resistance R ohm. And this I2, this actually again is divided in IC and in IL, where this is L and this is the capacitance of this capacitor is C. Again, when it will come back, it will see that this over here, it will be IC, the IL will come at this junction, we shall get this current as IL plus IC. The value of IL plus IC is simply equals to I2, so at this area we will see the I2 amount of current flowing through. Again, after this junction, we shall see that this I2 plus IR will be over here, which implies that the current I will be then passing through it, right? Now to understand these concepts, let us first of all try to find out the impedance for this circuit, because this is not very easy. As we have seen the impedances in the case of like a series combination, this is simply different from that. This will be for, say, over here it will be for the parallel circuit, right? So to understand the impedance, let us first of all come to the phasor diagram. The phasor diagram will be as such for this scenario is if we do take that this resistance, for this resistance, the voltage and the current are at omega equals to 0, which means of sine 0. So there will be this V and IR will lie over on this axis. Say for example, this is the x-axis. So let us first of all take that this is, say for example, IR, and this entire from over here till over here, this will be the voltage for this LCR. Now as we know that the current in the case of an inductor, it actually lags behind this voltage, because see, this voltage will be the same for this resistor, for this inductor as well as this capacitor, right? So if this is the voltage, the current, if it lags behind, obviously then the IL will be on this side, and we know that for a capacitor, the IC or the current through this capacitor, this actually will be leading by an angle of pi by 2. So over here we could say it as, this will be, say for example, IC, and let us check that over here this will be, say for example, IL. Now if it is taken for consideration that over here XL is greater than XC, which obviously indicated that the reactance for this like L or this inductive reactance is greater than that of the capacitive reactance, and obviously we could say that this IL will be greater than IC, right? So it will be this over somewhat here, it will be the IL minus IC, right? So by the vector addition of IL and IC, we can see that it comes to IL minus IC. Again we do see that there we need to have a vector addition of the IL minus IC component with the IR. So applying the parallelogram law of vector addition, we obviously could say that this is the actual current that is flowing. So let us say for example, take it as IS, and obviously it will be lagging behind by a certain degree, say 5, right? Now applying this concept of this phasor diagram, we can do that this IS, we can actually write it as see, this IS is a vector addition for which one? For this IR and IL minus IC, right? And what is the difference between this IR and IL minus IC? Simply it is pi by 2, right? So applying the Pythagoras theorem, we can write it as this IS will simply be equals to IR square plus IL minus IC whole square, right? Now over here, if we actually take the concepts of impedances, we could say that this IS, it could be stated as the voltage difference or the potential drop of this VLCR, and this VLCR will be the same for this R, L and C, since all are connected in parallel. So we can write Is as V divided by, this V is actually VLCR or this V, right? Divided by, let us take the impedance of this entire circuit, because Is is responsible for the entire circuit. Likewise, this Is will be equals to the potential drop across the entire circuit divided by the impedance for the entire circuit, right? So we can state it as V divided by Z is equals to under root of, now what will be Ia? Simply Ia will be equals to this V divided by R, right? So V divided by R, and it will be whole square plus. Now what will be IL? IL will simply be equals to this V divided by this XL or the inductive reactance. So this will be V divided by XL minus IC likewise will be V divided by XC, where XC is the capacitive reactance, right? Now over here from this expression obviously we can check out V as common. The V square taken out common, this will come outside of the root over, and it will see the expression will be likewise. V divided by Z will simply be equals to V multiplied by under root of 1 divided by R whole square plus 1 divided by XL minus 1 divided by XC whole square. Now we could cancel out this V with this V. We will be finding out the expression as that 1 divided by Z is simply equals to under root of 1 divided by R whole square plus, we can write XL as equals to omega multiplied by this L, right? So this will be 1 divided by omega L minus, now what is the value of XC? As we have seen in the previous lectures, that XC value was simply equals to 1 divided by omega C. So 1 divided by omega C, which means that the denominator of the denominator will simply be the numerator, so it will be coming likewise. So we have found out an expression for the reciprocal of the impedance of this LCR circuit, right? Now it may be noted the admittance, the term, is simply equals to the reciprocal of the impedance. Right? And again we can come to the concept that the conductance is simply equal to 1 divided by the resistance. Right? And the susceptance will simply equal to 1 divided by the reactance. Now what is admittance? Say for example, if we take the impedance or the resistance as something which will oppose to the flow of the current, the admittance or the conductance or the susceptance will actually mean that how much we are allowing the current to flow through, right? This term of admittance as 1 by impedance will simply be equals to 1 divided by Z. This one, the conductance of 1 by resistance will simply be equals to, for this term, for this particular resistance, and the susceptance R for the L and for the C. For the inductance it will be, for the inductor it will be 1 divided by omega L, and for, say for example, this capacitor, this will be equals to omega C. Right? So we could write as this expression as equals to the admittance of this LCR circuit in parallel will simply be equals to under root of the conductance square plus the square of the value of the difference between the susceptance of the inductor and the capacitor. Now whichever is greater, it will win, but the value will simply be positive, right? We have taken the case over here that XL is greater than XC, right? Likewise, we have drawn the phasor diagram. Now, taking this into concept, if we do wish to find out the graphical representation of the admittance, whose actual like this will be, this side we are taking on the y-axis as admittance, and over here we are taking, say for example, the frequency. Say this is the frequency and this is the admittance. We actually represent this admittance as y, which is equals to 1 divided by z. So, looking into this expression, there will come one frequency for which this 1 divided by omega L will simply be equals to omega C. Why? Because we know that omega is simply equals to 2 pi f, where f is the frequency of this power supply of SC, and there will come a point when the susceptance for the inductor will simply be equal to the susceptance of the conductor, right? Because as we have said, say for example in Lc oscillations, that for 1/2 cycle the energy actually, like this capacitor, de-energizes and the inductor is getting the energy. But for the other half cycle, which will be seen that this inductor then will be de-energizing and this capacitor will be energizing at that point of time, right? So applying these concepts over here, we will see, say for example, we are taking, this will be the graph for the susceptance of the inductor, which simply is equals to 1 divided by omega L. Now, the susceptance for this capacitor will simply equals to omega C, right? The graph for the omega C, it will look like this. So obviously, if you do note, over here we have got a particular point for which the susceptance for the inductor is cancelling out the susceptance of the capacitor and vice versa. So if we do actually put out a projection on this x-axis over the frequency, we will be finding out that this is actually FR, or the resonant frequency. Now actually theoretically when we will find out the resonant frequency is that for finding out the resonant frequency, the term or the condition applicable will simply be equals to 1 minus omega L, or so 1 divided by omega L minus this omega C has to be 0 because they are cancelling out, which implies that 1 divided by omega L is equals to omega C, which implies that omega is equals to under root of 1 divided by LC, because if we do cancel out, we will see that C is over here coming down and the denominator omega over here as square. So omega will be equals to under root of 1 divided by LC. And as we know that the value of omega, it is simply equals to 2 pi f, where f is the frequency of this alternating power supply. So we can say it as the f, or the resonance frequency at this particular point, will simply be equals to 1 divided by 2 pi Lc. So we have found out the expression for the resonance frequency over here. Now observe one thing very clearly. If this 1 divided by omega L is cancelling out omega C, which means that the susceptances are actually cancelling them out. And the susceptance could be regarded as that it is the property of a substance to actually make the inflow of the current through it. Now, if this susceptance becomes 0, if this entire term becomes 0, the only responsible for this impedance will be the R. Now if the susceptance becomes 0 over here, obviously we may say that the resistance is very high, is equals to infinity. How? Because susceptance is equals to 1 by the reactance. If susceptance equals to 0, which means that over here, say for example, if this comes out to be the 0, this reactance will be an infinite one. Which means that if the reactance is, for which part the reactances are applicable? On this particular part, right? Because obviously the reactances are not available beyond this R. This is simply about the resistance and the conductance, right? So if we do see that the reactance is basically equals to infinity, which means that it won't allow any of the current to flow through it. Which means that if we are keeping it also, at the time of this resonance frequency, actually no current is going to pass through it. So we could make an equivalent circuit to it as, this is the power supply, this is the resistance, and over here, no matter how much current you provide, it will be acting as infinite resistance. It will not allow any of the I to flow through it, which means that this will act like an open circuit. Having it over here or not having it over here will just be the same if the resistance or the reactance is simply equals to infinity, right? Which means that the susceptance is equals to 0. So looking at this, we can understand that this will actually act like an open circuit now, right? Why this is an open circuit? Because this over in this part of L and C, actually it is not allowing any of the current to pass through it, right? So actually it is not allowing any of the IL and any of the IC, right? Now observe over here that in this particular resonance frequency, the only responsible over here, see, the only thing responsible is R for the resistance, or 1 by R for the conductance, right? Now over here, this is for the admittance, right? And for the admittance, we are seeing that at this particular point of time, the admittance will be equal to 0, considering that there is no resistance, right? We have drawn the graph as there is no resistance. So the admittance at this particular point will be equal to 0, because the value of this one and this one, because this is simply equals to omega C, or the susceptance for this capacitance or the capacitor, they are simply cancelling out. So the Y at this point will be 0, right? So if actually there are no like resistance over here, which means that if the admittance is basically 0, over here the impedance will be infinite, and if the impedance will be infinite, then we know that I is inversely proportional to impedance, which means that the value of current will be 0, right? But yes, obviously 0 means what? The minimum. But obviously if there is a certain amount of R, we can see the graph as, over here if we take I, and over here if we check the frequency, at a particular point we shall observe if there is no R, this I will simply come to 0 at the resonance frequency. But if there is R, the I will be like this. So at this particular point, we could see that over here, the I is becoming the minimum. So this is the I minimum at FR, or the resonance frequency, when the arrangement is in parallel, right? So looking at this, we can say that actually we are making the I minimum, and likewise as in series combination of LCR, we know them as the acceptor circuits. This is the parallel circuits are also known as rejected circuits. So obviously over here we have understood that for XL greater than XC, what will be the phasor diagram? After the phasor diagram, we did find it out that what will be the 1 divided by Z, and 1 divided by Z is equal to the admittance, and admittance is simply equal to the reciprocal of this impedance. And also we have seen that how we could actually find out over here that if this part is equal to 0, we could find out the resonance frequency. And with the help of that, the graph is being drawn. We have seen that while on cancellation, the admittance at the resonant frequency will simply be equal to 0, which means that the impedance will simply be equal to infinity, which means that it will actually not be like it, the current will not be able to pass through it. But obviously, if there is a resistance, the current will pass through it, but at a minimum point at this resonance frequency, right?